Welcome to the explainer. So, imagine for a second that the universe, everything around us, literally including you and me, isn't just a random collection of particles. What if it's actually structured like a massive universal computer processor? In this incredibly fascinating framework called Logos field theory, physical matter and mass aren't just built-in properties of reality. They're actually complex data outputs calculated by a mathematical engine. Today, we're going to unpack exactly how this theory proposes to calculate the specific, actual masses of our universe's fundamental particles, from lightweight leptons to incredibly heavy quarks.
Okay, let's dive into this. Here is our roadmap for today. We're going to scale up, starting with the vacuum's base code in the universal rendering engine and the arithmetical ground state. Then, we'll see how it calculates lightweight lepton programs, look at phase dissonance, and finally compute the system-straining masses of heavy quarks.
All right, Section 1, the Universal Rendering Engine.
To even start calculating mass, we first have to deal with a massive problem, the quantum foam. It's this storm of infinite, chaotic fluctuations at the very tiniest scales of reality. Logos field theory tackles this head-on. As you can see, the theory uses what's known as the explicit spectral trace formula as a foundational noise cancellation filter. Think of it like a pair of top-tier noise-canceling headphones for the universe. It takes all that infinite, wild static of the vacuum and strictly maps it onto stable, geometric baselines.
Breaking down the mathematical mechanics of this filter, the LFT spectral partition function, we see it split into two absolutely crucial parts. Up top, the numerator compiles the complete Riemann Zeta function. You can think of that as our raw math input. And down below, the denominator houses the custom LFT Dirac operator, which acts as the system's rigid hardware filter.
Moving right along to Section 2, the arithmetical ground state. So what exact coordinate is this engine targeting? Reality's base code is anchored precisely to the first non-trivial zero of the Riemann Zeta function. And this brilliantly illustrates what happens when we evaluate the engine there. We get a mathematical clash. A second-order zero from our math input literally collides with a third-order pole from our hardware filter. This double pole collision completely strips away the infinite noise we just talked about, leaving us with a clean, single, static value known as a pole residue.
And that residue, it gives us an incredibly specific energy density, exactly 62.5013 gigaelectron volts. Under this logic, this specific number is the vacuum brick. It's the ultimate base hardware unit from which all subsequent physical matter is compiled. But, any heavy-duty hardware needs safeguards, right? Well, this base state mathematically derives the fine structure constant at exactly 137.036. In this setup, that famous constant acts like a perfect thermal fuse. It literally prevents the hardware of space-time from crashing into infinite processing loops, keeping the whole universe running smoothly.
Which brings us to Section 3, calculating lepton mass harmonics.
With our vacuum baseline firmly established, how does this engine actually compile lightweight data programs, like leptons? Let's trace the exact steps for deriving the mass of a muon. First up, the overtone mechanism models the muon not as a tiny dot, but as a complex string vibration buzzing at a 23.6742 MHz master frequency. Next, trace calculus expansion jumps in to strip away any vacuum interference. And finally, mass extraction isolates the precise, localized mass of the particle.
Now, what's really interesting about this slide is how these expanding harmonics actually operate. The first zero sets our basic electron baseline, but step up to node 2, and that second zero acts like a harmonic metronome for the muon, calculating a precise, localized mass of 105.78 MeV. Then, look at node 3. The third zero governs the tau lepton, and man, that demands extreme processing power to calculate a much heavier mass of 1775.8 MeV. Let's look at the consequences of that in Section 4, phase dissonance and decay.
So what actually happens physically when you push a universal processor to these extreme overtone limits? You get phase dissonance, because keeping up those extreme muon and tau frequencies demands massive data throughput. A mismatch starts building up between the particle's localized calculation and the universal master clock. This creates severe computational drag. And here's the kicker. In this framework, that computational drag is exactly what manifests as physical inertial mass.
Eventually, that dissonance is going to hit a critical limit. To avoid a localized system crash, the processor basically forces a terminal packet drop. It rapidly sheds all that heavy processing burden and collapses back to a stable ground state.
And what does that look like to us in reality? We observe it as the rapid decay of muons and taus, straight back into stable electrons.
All right, Section 5, Computing Heavy Quark Masses. It's time to shift gears entirely and see how the universal rendering engine handles the extreme computational burden of heavy quarks. To do this, the math architecture completely transforms. See, leptons flow smoothly in a two-adic space, but quarks carry color charge, which forces a hard shift into the three-adic sector. Suddenly, the engine isn't processing binary anymore. It has to process ternary quantum logic, creating immense geometric resistance.
Let's move to and see how this builds. Because quarks are mathematically bound to these complex cycles, this resistance creates what the theory calls color-induced torsion snags. These octonic snags rigidly lock the data boundaries in place, and that structural stiffness mathematically produces the exact tiny mixing angles we actually measure in the CKM matrix. It's truly wild.
So how does all that translate into actual quark mass? Well, the engine uses the Adelic shell theorem, which acts almost like a giant funnel of processing lag. The light up and down quarks sit comfortably in shallow nodes, very small computational invoices. But as the formula forces its way into deeper p-adic modes, the resolution lag becomes severe. The bottom quark exponentially inflates to roughly 4.18 GeV just to resolve its code. And then we hit the absolute bottom of the funnel.
The top quark. This is an extreme multi-base column of data that borders on an all-out algebraic overflow error. It is the absolute limit of the processor. To successfully calculate its mass without crashing the universe, the trace formula has to securely evaluate this code against the unramified intersection locked to the Higgs invariant boundary, which sits at roughly 125 GeV. So the crucial point is the result, 172.51 GeV for the top quark. Under Logos field theory, that isn't just a random variable. That staggering weight is literally the final computational invoice billed by the global engine. It's the massive amount of energy required just to anchor that highly complex color torsion code into our physical reality.
Bringing it all together, this comprehensive equation tree shows the whole shebang. It recaps how a single spectral trace formula acts as a universal compiler by targeting different mathematical geometries, scaling up from deriving the vacuum baseline to calculating precise lepton harmonics, all the way down to those massive quark shell masses. The entire spectrum of fundamental mass is explicitly calculated.
Which leaves us with a truly provocative question. If this theory holds true, are the fundamental limits of our physical reality ultimately just the rigid boundaries of prime number topology? It suggests that the everyday mass we interact with might just be the elegant byproduct of a sublime mathematical engine. Thanks for joining me on this explainer, and keep questioning the deep code of our cosmos.